Assalamu alaikum wa rahmatullahi wa barakatuh. This is the third part of Chapter 8, Newton's Laws. At the end of this video, you are going to be able to state and apply Newton's second law on a system. It's good to remember first the main idea that we have mentioned in the last video. We distinguished between inertia and mass. We stated Newton's first law and Newton's third law. In this video, we are going to talk about the fundamental principle of dynamics, which is the second law of Newton, which states that the acceleration is directly proportional to the net force applied and inversely proportional to the mass of the object. It's good to remember first what we have mentioned about the first law of Newton. We said that when forces are balanced such that the sum of forces external or the net forces is zero, then we have either one of these two cases. Object is at rest and it stays at rest, or object in motion and it stays in uniform rectilinear motion. What if the net forces are unbalanced? There will be acceleration. But let me ask you a question, and I'm sure you are going to answer it. On which two factors do you think the acceleration will depend on? Here comes the interesting part. Let's remember the two blocks we have talked about in the last video. We applied equal forces to both of them. Do you remember which one was faster to move? You are following up with the lesson in a distinctive way. First, we have that mass of A is greater than mass of B, and we applied equal forces. Then the tiny block will have more acceleration. Now, what if I have two equal masses? We are going to apply different forces such that the force acting on A is less than that one acting on B. In which case do you think the acceleration will be more? Of course, the one in which the force was more. And we can find that the acceleration of B is greater than that of the acceleration of A. To draw a conclusion, let's answer this question. What are the factors that affect on the acceleration? We found that if the net force is more on the same mass, the acceleration is more. Thus, we can say that the acceleration is proportional to the force. While if the mass is greater with constant force, the acceleration is smaller, then they are inversely proportional. Mathematically, it can be written like this: A vector equals to the net force vector over mass. In simple terms, the acceleration is directly proportional to the net force applied and inversely proportional to the mass of the object. Some people like to write it like this: F vector equals A vector. The net force is the product of the mass and the acceleration, where in SI units, F is in Newton, mass in kilograms, and the acceleration in meter per second squared. It's important to state that first law is a special case of the second law where the acceleration is zero. In fact, time equations of motion helps us a lot in solving problems in Newton's laws. So let's remember, for uniform rectilinear motion, x equals to vt plus x0, where v is constant, the acceleration, which is tangential, equals to 0 meters per second squared, A vector dot v vector equals to 0. While in uniformly varied rectilinear motion, the time equation of x equals to half at t squared plus vt plus x0, while v equals to at times t plus v0, and the acceleration, which is the tangential acceleration, is constant. Remember that A vector dot v vector is positive, means the motion is uniformly accelerated rectilinear motion, and when A vector dot v vector less than 0, the motion is uniformly decelerated rectilinear motion. At last, V final squared minus V0 squared equals to 2AD, which we call it the time-independent equation. Let's solve this application. Ali pulls his brother Hassan, who is sitting on a sled on horizontal icy ground, by means of a massless rope, which makes an angle of alpha equals to 60 degrees with the horizontal. Given the friction force acting on the sled is 40 newtons, the pulling force is 100 newtons, the system S, sled, and Hassan has a mass m equals to 20 kilograms. G equals to 10 meters per second squared. It is preferred to pause the video after each part of this question and think of the answer before we give it to you. The first question, name the forces acting on S. Since there is a mass for the system, then there is weight. We have support, so we have normal reaction and vector. There is friction and the tension of the rope T vector. Question 2. Represent, not to a scale, the forces acting on S. Take a look at the figure and let's check the representation. First, draw the XY axis. Then, we know that N is vertically upward perpendicular to the support. Weight is vertically downward. Tension along the rope. And friction is backward against the tendency of motion. Question 3. Write the expression of X and Y components of these forces. We represented them in this table. mg, since it's vertically downward, then its X component is 0 and its Y component is minus mg. N vector is positively upward along the Y axis, then its X component is 0 and its Y component is just n. F vector is minus f, since it is opposite to the X axis, while the Y component is just 0. What about the tension vector then? Its X component is T cosine alpha and its Y component is T sine alpha. Is there a motion along Y-axis? No, there's no motion on Y-axis. Then, can we say that the forces acting on S are balanced along Y-axis? Yes, since there is no motion. Which law of Newton describes best the motion along Y-axis? Great! Newton's first law. Deduce the magnitude of the normal reaction force. They said deduce. It means that the previous questions will help us. Actually, the normal force is along Y-axis. And we said that along Y-axis there is no motion and we can apply Newton's first law. Then, according to Newton's first law, we state the components of the forces along Y-axis, writing their projections along Y as minus mg plus n plus 0 plus t sine alpha equals to 0. Therefore, n is mg minus t sine alpha, replacing m, g, t, and alpha by their values. Finally, n is 113.4 newtons. Question 8. One claimed that in a horizontal motion, mg always equals to n. Discuss. What do you think? Actually, this statement is not always true. Counterexample. In our horizontal motion, mg equals to 200 newtons, which is greater than 113.4 newtons, the value of n. Specify which law of Newton describes best the motion of S along x-axis. It is Newton's second law, since the x components of the forces acting on S are not balanced. Like that, mgx plus nx plus fx plus tx equals to 0 plus 0 minus F friction plus T cosine alpha, and writing their values, it is 10 newtons and not 0. Question 10. Deduce the acceleration along x of s. Again, the question is deduce. We have just mentioned that the forces along x-axis are unbalanced. Then, according to Newton's second law, the sum of forces equals to mg vector plus n vector plus f vector plus t vector equals to ma vector. Then along x-axis, the addition of the forces along x as 10 equals to the mass times ax, and the mass is 20. Therefore, ax equals 10 over 20. It is 0.5 meters per second squared. The last question. Deduce a vector, the acceleration of s. The acceleration then is just along x-axis, and it is written as 0.5 I vector. The last idea to mention is tensions on a rope of negligible mass. Consider a hand pulling a mass arm by means of a rope of negligible mass. Take this sample question. What is the relation between T1 and T2, where T1 is the force of tension acting on the hand and T2 is the force of tension acting on the block of mass M? We're going to take the rope as the system to study and state the forces acting on it. We have the force exerted by the hand on the rope and the one exerted by the block on the rope. Using Newton's third law, we know that the force exerted by hand on the rope is equal to minus T1, which is indicated in the figure, and the force exerted by the block on the rope is minus T2. Using Newton's second law, sum of external forces equals to ma vector. These forces are minus T1 vector plus minus T2 vector equals to ma. Be aware that we placed the forces acting on the rope by minus T1 and minus T2. The rope has a negligible mass, therefore it is written as minus T1 vector plus minus T2 vector equals to 0 vector. Finally, T1 equals to minus T2. The conclusion states that the tension force has the same magnitude at all points of a rope of negligible mass. These are the main ideas of the last two videos. Study them well and, as usual, take notes. This is the end of part 3. Thanks for watching.